So welcome back, and to the new session on Physics 4480. And today's topic is essentially Wick's theorem and the proof of Wick's theorem. And we are going to wrap it up, and then we are going to move into something which is called Wick's generalized theorem, which we will find very handy for calculations. And it's going to be particularly handy when we are going to change the reference state from the pure vacuum to a user-defined vacuum, which we normally call a reference state, which then could be all the states which are being filled up to the Fermi level. And that will define a new vacuum state. And you will see why this is a handy way of representing the calculations and having this as a calculation recipe. Because what happens is that as soon as you are getting into more than 3-4 particles and you want to calculate expectation values, you will quickly see that the benefit with Wick's theorem, is a little bit, spoiled, because you need to take into account all possible contractions. Redefining the vacuum allows you to be able to handle systems with many, many particles. And then we will deal with something which are called particle hole excitations. And that's the way we will discuss the physical systems in terms of particle hole excitations. So that introduces a whole set of language and jargons, which we will use repeatedly. But the first thing we need is Wick's generalized theorem, and then we need also to prove it. So I just wanted to remind you quickly of some of the practicalities and some of the things which we went through last week. So today is essentially Wick's theorem and Wick's generalized theorems with examples. And then tomorrow, hopefully, we will also look at a diagrammatic representation. And then we are going to start scratching the surface of this particle hole formalism. That depends on how fast I move. I tend to be slow normally. And much of these are things which I haven't wrapped up in terms of latex notes. So you will have to suffer my handwritten notes. But you can find the notes on the at the GitHub address of the course. And then there is an exercise. And I wanted to say something about this exercise as well, in order to guide the eye a little bit. So this exercise is about a model which was introduced in the 60s by Lipkin and company. And it's a very, it is a model with lots of pedagogical features and interesting pedagogical features. So one, we can calculate expectation values. We can rewrite the Hamiltonian in terms of the quasi-spin operators, which you see here. It's a system where you now have only 2 levels. So you have one level where the spins are down, and each slot here, 1, 2, 3, 4, can represent different quantum numbers. But all these states, 1, 2, 3, 4, which you see here, they have in common that they have a spin down or spin up. This is up to you to choose whether you want to have spin up or spin down. So here we just label it with a spin up. And then you can excite the system. So if you assume that this is your ground state, then you can excite a particle up to an excited state. And then you could have one where the spin is being flipped. And the thing which is interesting here is that this example, this model, you can set up a matrix you can diagonalize and get all the eigenvalues. If you have 2 particles, you get a 3x3 matrix, which is easy to diagonalize. You can actually find analytical eigenvalues. If you have 4 particles, you're going to get a 5x5 matrix, etc., etc. The thing which is useful here is that it allows you to gain a very good pedagogical insight about the first method we will encounter, which is full configuration interaction theory. And then you can also obtain analytical expressions for what's called Hartree-Fock theory, which is a mean field method, which is pretty close to the philosophy of density functional theory. So you will see us actually reusing this model again and again and again. Now, this model has also received a kind of new how to say, era, in the sense that you can rewrite the Hamiltonian now in second quantization in terms of this quasi-spin operators. So these actually behave like the standard quantum mechanical spin operators. Now, when you have rewritten it like this, you can actually tailor it for quantum computing. So people have, since you write the Hamiltonian in terms of Pauli matrices, people have actually used this model here to simulate it on quantum computers. So it's a system which has gotten, as I said, a revival, not only because it's pedagogical, it's very useful, it illustrates many of the basic concepts, and you will see us reusing it again and again. And so hopefully that gives you guys a little bit better understanding of many of the many-body methods. And at the same time, if you're taking this course, which is called Physics 5419 in the spring, we're actually going to model this using algorithms for quantum computing. So it's a very useful method. So there are very few such methods which allow you to catch many birds with a stone. Many birds with a stone is a pretty violent thing. I think I like better the Norwegian one, to take a fly with not two flies with one catch. In Italian, it's actually different. That's actually to catch two pigeons with one beam, which is also less violent than just killing two birds with a stone. Okay, guys. So let's bring back what we had last week and bring it up, and then move over to the whiteboard and look back at the derivations of Wick's theorem. So let me quickly remind you from the whiteboard here what we did last week. So we had a chain of operators. So Wick's theorem simply states that with a chain of operators, you can then calculate. So if we go spool back a little bit and look at the theorem itself. So what the theorem says is that the expectation value of a chain of creation and annihilation operators can be rewritten in terms of the normal order product of all the operators, the normal order product of all operators with one pair which is being contracted, then two pairs which are being contracted, and then this continues till all pairs being contracted, which means that you need to have an even number of creation and annihilation operators, because else you will always have a standalone creation and annihilation operator, which then will give you automatically zero. So just remember also that when we write it like this, x, y, z, w, what we are doing is to calculate an expectation value. And what we end up with, for all practical purposes, is the sum over all possible contractions, where all the operators are contracted, because all the other ones lead to something which ends up being zero. So when you do that, in order to prove it, we needed a lemma. And this lemma now goes as follows. If we have proved it for a given number of operators, so suppose n operators, if we then add one operator, we can actually rewrite it like this. And this allows us then to extend it to n+1 operators. So what we're going to discuss now is a little bit the implementation of this and the consequences of it. And then we go back to Wick's theorem and show that if we have proved it for n operators, then this applies also for n+1. So this is done by induction. That's the standard way by which you do Wick's theorem. And we have showed it by practical calculations with examples for 2, 3, and 4 operators. That's what we did last time. So that means that if we now assume that 4 is equal to n, then if we can then prove that it applies for n equal 5 or n+1, then this should apply for all possible numbers of operators. So this is basically where we ended last time. And what we said is that this lemma is valid immediately if omega is an annihilation operator, since then, so the one we add is already normal order. So that just follows immediately. And then we have assumed that the sequence, which you have here, is normal order. So because we have n here. And if omega is a creation operator, we need to prove the lemma if all x, y, omega are annihilation operators. Because if we have if all of them are creation operators, then the contractions are immediately equal to 0. So we need to prove it in case they are annihilation operators. And in that free, what we do then is that we anti-commute it through all x, y, z, w's operators, and then they get the first term, and then all anti-commutations which are then produced give the second term of the lemma. So let's see that with some applications, with some simple examples. And then we generalize it to n+1 operators. And then when we've gone through these examples so that you get a feeling of the lemma, then we go back to Wick's theorem, and then we can show Wick's theorem with that lemma. And when we have the Wick's theorem, we can then go to Wick's generalized theorem, which is going to be extremely useful for us when we are going to run calculations. And you will see why when we also introduce these particle hole calculations. So let's go back to today's material. And there should be a notebook here, which we can start with. So let me just do that after these preliminary words. So let's look at the consequences of this additional lemma. So let me just restate the lemma. So what we are saying then is that if we have a normal ordered chain already of a set of operators x, y, z to some w, and we add a new operator, then this can be written as the normal ordered chain of operators x, y, z of w and omega, plus the sum over all the contractions of these operators with a newcomer. So when I mark it like this, it means that the other operators are contracted only with the newcomer operator, the newcoming operator. So we would have x, y, z, and this goes like an omega. And then I indicate this, that these operators are contracted with omega only. So this is what the lemma says. And let's take a look at of these statements 3 and 4, which we had last week. So I'm going to refer then to what we wrote last week, examples of this statement 3 and statement 4, where we now are looking at the case where the new operator is a creation operator. So what we want then, if we now assume that we have a chain of the operators A1, A2, up to some AK, and then we multiply this with an AL here. So we said that the chain of operator has to be a chain of annihilation operators, and this is what we need to prove, because if these are creation operators, this is automatically 0 when we calculate an expectation value. So if we do that, what the lemma says is that we can rewrite this as an n of A1, A2, up to some A. Let's just put an AN, so we have n operators, and then we have an AL here, plus, and this now contains a sum over all the possible contractions of these previous operators of A2, A of n, with this operator A of L. I just indicate that in this specific way. So let's assume now that we put n equal to 1 here. So we have only one normal ordered operator. And let's see what kind of results we get then. So that means that if I put that, then I have the following. I have an A1, and then I have an AL. And we know we can rewrite that one as the normal order product of A1, AL, dagger, plus the contraction, which is also normal order of A1, AL, dagger, like this. And we know that this gives us then, when we look at the calculations, we get the normal order product of the first one, which is simply now the expectation value of 0 of AL dagger A1 is 0, so we have a minus sign, plus the A1, AL, the contraction here, dagger. So if L is different from A1, this is automatically 0. Else, this is actually the lemma for K equal to 1, no, N equal to 1. So we have only one annihilation operator. So you see the way you would set it up in that specific case. And this means that if we have a chain of operators here, which is normal order, in this case only one, you see now that using the standard approach with Wick's theorem, actually this operator, when I now want to calculate an expectation value of that. So if we calculate the expectation value, we have 0, A1, AL dagger, 0. And then this is just us setting in the commutation rules for fermion operators. So this is equal to delta IL minus, and then we have 0, and then I have AL dagger A1 of 0. So when we calculate this quantity here, this one, this is the same as us setting up this guy here. Doing that gives us this term, which is this. And then we have the normal order term, this one, which we wrote like that, which is simply this term which you see here. So for n equal to 1, we see that this lemma holds. Okay? So this is just us trying to demonstrate that the lemma does make sense. So if I then assume that I have assume now that it holds for, let's say, n operators, then if it holds, for n, it should also hold for n plus 1. So this is about the lemma. So let's take a look at that one. So what we do now, we just multiply from the left with a new annihilation operator. From left with an operator A0. So what we have then is an A0. And then we have a normal order product. So the assumption now is that this chain is normal ordered. And then I have my AL dagger. So what I'm saying is that if I go back to the lemma here, what I'm saying now is that I am multiplying it with an operator. If this is an annihilation operator, then this is automatically 0. If it is a creation operator, we now have to be a little bit careful. And this would be n operators, and then we just add this one. But now this should also hold for us adding another operator here. So we have n plus 1, and then we multiply that one with this operator. So if the lemma holds for that as well, then we can use that immediately into Wick's theorem, and then we can prove Wick's theorem. So let's continue then, and just manipulate this expression here, because this expression here, when I now use this lemma, so this should simply give us something which runs like A of n of A1, A2, up to AN. And then we have this term normal ordered, plus the sum over all possible contractions, where I just multiply this one with the lemma. And then I have an A1 up to an AN, and then I have this AL, which I'm adding. And these operators are contracted with that one. So if we look at the term, the first term, what we have then, we have that this term, A0 of n of A1 up to AN of AL dagger. Since this is a annihilation operator, then this is automatically given by a product of A1, A0, A1 up to AN multiplied with AL dagger. So this is our A0. So because this is already normal order, if you take this product here, I can always rewrite that one. Since these are annihilation operators, they're all the same, then it doesn't matter which order they come into. So I can always rewrite this term, which you see here, this one. Since they're all equal, I can always rewrite them as a normal order product. And then you can reshuffle them as you want. Okay, so that was the first term. Let's now look at the next term. If we look at the term which runs like this, sum over all possible contractions, what I would have then is A of n of A1 up to AN, and then I have my AL, and this is contracted with the final one, which be the creation operator. It's easy to see that we can actually rewrite that one in terms of sum over n, but now we have A0, and that is not contracted with AL, but we have all the other ones, A1, A2, up to AN of AL dagger, but the contractions take place here. So this is not involved in the contractions. Okay, but I can always set it up as a normal order product. So what I need to do next is actually to manipulate this term a little bit. And if we do that, what we can see then, if we look at the last term, so the last term, if we just take it out, then we can rewrite that one as a minus of n. So we anti-commute the AL. So since this is a normal order product, so just keep that in mind. So we can rewrite that one as an A0 of AL. So just keep in mind that this is a normal order product, so we can always interchange this AL plus. And I can rewrite it in terms of this term here, where I now have the A1 up to AN. So I'm just reshuffling the order of the operators, because these are normal ordered operators. And that means that when I look at this one, I can rewrite that again as a -1 to the power of n. And then I have a normal order product of A0, AL dagger, and then plus the contraction of A0 of AL dagger, multiplied with this product of n of A1 up to AN. This is just a normal order product. And then I know that this n of A0, AL dagger, that is simply the same as minus n of AL dagger of A0. And then I can use that one to simply reshuffle that equation here, so that what I end up with is, if I look at the final term, so the contraction here simply says that A0 has to be equal to AL. So that would be the one contraction which I have. And I can actually reshuffle everything here in terms of minus 1 over n of AL dagger, A0, and up to AN here. So that means that I can actually rewrite that specific term which we have in the following way. So let me just do that. If I now insert this one, so we can rewrite. And then I have my A dagger, AL, multiplied with this product here of A1 up to AN. This is now the same as a normal order product of A0, AL dagger, and then I have A1 up to AN, which again then is the same as minus 1 over n for the normal order product of this A0, A1 of AN of AL dagger. And if I bring it back, what we have then is that when I put this back into the lemma, then I have that this A, if I just do that, of N of A0, A1, of AN, of AL dagger, that is the same as the normal order product of A0, A1, up to AN, of AL dagger, plus the sum now over all possible contractions with these operators, A0, A1. So that's the new chain of operators which I have by multiplying with A0 of AL dagger. And now I have all possible contractions here. So that is a demonstration that the lemma holds when I just multiply from the left with one operator, an annihilation operator. If these all are contraction creation operators, then this is automatically zero. Now, the next step is actually to go back to Wick's theorem. Because then Wick's theorem, if it holds for n operators, what we need to use now is actually this lemma. So I have the chain of operators, and this is now multiplied with a new one, omega. And that means that if I insert that one into Wick's theorem and use the lemma first, or if we use Wick's, so we would have n of x, y, of z, of w, multiplied with omega, plus the sum over all contractions here. So I would have n of x, y, z, of omega. So I'm now multiplying, adding this. By the way, this should actually not be that. So I'm just bringing this back into Wick's theorem. So it means that I get w of omega plus, and then I have now all the contractions where these operators are contracted, one, and it does not include omega, and plus the one contractions. So this is just us applying the lemma of z of omega. So it does not include a contraction with omega, and now we contract with omega. And then we do the same thing with two contractions. We have one which excludes omega. So we have n of x, y, z, of w. So we have the set of two contractions not involving omega. And then we continue, and then we have including omega. So we have now a set of contractions here where one of them includes omega as well. And we can continue this way till the final ones. So let's just do that. And then we end up with plus, and then we have n divided by 2. So that's the original number which we had of operators. And we are going to have a sum which excludes omega because we have multiplied with omega from the right. And I'm just writing this in terms of dots here. And then we have a new term of n divided by 2 here, where we include omega. And then we have n of x, y, z of omega. And now we include omega, etc. And then we have a final term because now we add one operator. And then we have to be careful whether we have an odd or even number. So if n plus 1 is an odd number, that means that n plus 1 will always give 0. Because if that's an odd number, then if n plus 1 divided by 2 gives us an odd number of n plus 1 divided by 2 gives an odd number of operators, there will always be one which is not contracted with the other ones. And then we would have here with different, not including omega. So I just write it in a more compact way here of n plus 1. And this includes omega. And whether if omega or if n plus 1 gives an odd number, then we always have one operator which is uncontracted. Then we end up with one operator which is uncontracted. Which gives a zero expectation value. Then, if we also look at the sum here, so we have the sum over all the possible contractions, where they are different from where they don't include omega. And if I then add the one over the possible contractions where we include omega, we can simply rewrite this as the sum over all possible contractions. So that's not so difficult to show. So when that is the case, what happens then, if Wick's theorem applies to n operators, if we add one operator, it also applies. So that means that our chain of operators, x, y, z, to w, which is the n chain of operators, and if we multiply with a new one, then this can then be rewritten in terms of the expectation value over all the possible contractions. So that is n divided by 2, so that's the number of operators now. This is normal ordered. And then I have x, y, z of omega, of w or omega. And then all operators are being contracted. So all contractions. All contracted. So this is a final quantity which actually gives us something which is non-zero. So Wick's theorem is in a way extremely compact. And it allows us to set up and perform calculations by simply having to evaluate that final term. Now, there's one thing in an example here which I wanted you to note, which also leads to Wick's generalized theorem. So let me just show that with an example, and then we can motivate Wick's generalized theorem. So example that motivates Wick's generalized theorem. And then I will state it after the example. So Wick's generalized theorem. Suppose we have a state, alpha 1, alpha 2, which is given by A alpha 1 dagger, A alpha 2 dagger, and this acts on the vacuum state. Now, if you look at these operators, they can be thought of as a chain of normal ordered operators. So this is a kind of a little bit sloppy formalism and sloppy language. So you will often see this as normal ordered, although what we are thinking of strictly in the previous examples, the way we used it, this was an expectation value. So now we are using this normal ordering in a slightly different way. Because the example which we had here, this means that we actually are calculating an expectation value. But the way I'm writing it here has a different meaning. What I'm simply saying is that these operators are now being normal ordered. And I will skip this kind of strange notation, but you can think of this as already being in a normal ordered form. Because we have all the creation operators, so you could actually claim that this is a normal ordered chain of operators, since we only have creation operators. If we now go over to the brass state, if we take alpha 1, alpha 2 here, this is the same as A alpha. So let's just put that one like this. So we have A alpha 2, A alpha 1. So what we could say, if we still use this kind of sloppy notation here, is that this is also a normal ordered set of operators. If we then look at the Hamiltonian, which we had for the one-body case, this is something which we can write as an alpha beta and A alpha, and with a given integral here of A alpha beta of A beta. This operator, as you see it, is already normal ordered. because we have a creation operator to the left and an annihilation operator to the right. So we would say that this operator here is also normal ordered. So what does this mean when we now are calculating expectation values? So let's suppose that we want to calculate this expectation value, alpha 1, alpha 2 of H0 of alpha 1, alpha 2. Now, the way this looks like is as a sum of alpha, beta. We have the integral alpha H0 of beta, and then we need to evaluate this quantity here, which is A alpha 2, A alpha 1, A alpha dagger, A beta, and then A alpha 1, A alpha 2, and then it's multiplied with 0. So the only thing we need to think of now is actually the expectation, the vacuum to vacuum expectation value. We just leave the other terms and we just look at that one. So let me just wait here so people get some time to write. So let me just move on. So what we end up looking at is A alpha 2, A alpha 1, and then I have A alpha, and then I have my A beta, and A alpha 1 dagger, A alpha 2. Now, when we use Wick's theorem, the only term which survives is the term where all the operators are contracted. And normally we skip the cases where we know that the contraction gives 0. But you should note one thing, and this is what leads to Wick's generalized theorem, that if I calculate, this is an accepted contraction, right? But what's the value of that one? So yeah, that's 0. Because just remember now that if we have A alpha, A beta, this one gives us delta alpha beta. And then if I have A alpha, A beta, this contraction is equal to this contraction. And this is equal to A alpha, A beta. So all these contractions are 0. Wick's theorem says that we run over all the possible contractions. But normally, when we do the calculations, we never list these because it's obvious. We don't list zeros, right? So if you look at that contraction, that is automatically 0. If I look at this contraction, this is also 0. This contraction is also 0. So what you see here is that the contractions within the operators and the states which we have defined, the contractions within these are 0. So the objects which we have been looking at, like this object, is already normal ordered. So that means if I take a contraction here, that is automatically 0. So when we have a normal ordered quantity, if we then look at the contractions which we can make within that normal ordered operator, that will always be 0. So if we perform a contraction within the operator itself or within the state here, that's always 0. Okay? So what we could do now, and since we know that what the answer is, so if I take this set of operators, I know that there are only 2 possibilities, which we calculated last week. So let me just list them for the sake of completeness. So what happens is that this is a viable contraction, this is another one, and then we have this contraction here. So that gives us a delta alpha, alpha 1, a delta beta, alpha 1, and multiply with a delta alpha 2, alpha 2 here. So that's one possibility because alpha 1 and alpha 2 are different. So if I take a contraction between alpha 2 and alpha 1 here, that is automatically 0. So that means that the only other possibility which survives is alpha 2, alpha 1, And then I have an A alpha dagger. Let me just write them up again, because this becomes also useful when you're calculating the expectation values for this Lipkin model in the weekly exercise this week. So the other contraction which we have is us having alpha 2 going here, and then we have beta going to alpha 2, and now we have an alpha 1 which now simply crosses a line, and then it crosses a new line, so minus minus gives us plus. And this would be the term which has delta alpha, alpha 2, delta alpha, no, sorry, beta, alpha 1, alpha 2, and delta alpha 1, alpha 1. And these are the two only terms which survive. Now, what is interesting now is that we can write this as a product, or it's actually an expectation value of normal ordered operators. So we have chains of normal ordered operators. So if you look at the expression which we have here, we have said that this is a chain of normal ordered operators. This is another chain of normal ordered operators. And this would be another chain of normal ordered operators. So the way we can write this is in the following way. So you can think of what we are calculating now as a normal ordered product of alpha 1, alpha 2, a normal ordered product of A alpha 1, A alpha dagger, A beta, and normal ordered of alpha 1 of alpha 2. So you can think of each of these quantities which we now are including in the expectation values as quantities which all are normal ordered. And what you see is that the only contractions, the only non-zero contractions, are those where we contract operators from different chains of normal ordered operators. So that leads to Wick's generalized theorem, which states the following. So let me just write it down so I have it properly. I don't say something stupid. Just quickly remind myself of that. So if you see what we have here, we would have this one linking to that one, and this one linking here, and this one linking to that one. That was one of the contractions. So this leads to what's called Wick's generalized theorem. So that means that an arbitrary product, so let's write this down and then we take a small break. An arbitrary product of creation and annihilation operators and annihilation operators so an arbitrary chain of in which some operators are already in a normal ordered form. In a normal ordered form. Is then given by, so let's just write it then as follows. So let's do that. So we have n of A1, A2, etc. And then there is a product of n of normal ordered operators, B1, B2, etc. And then we have a new normal ordered set of operators of C1, C2, etc. So this is a chain of operators. This can actually be written out as n of A1 A2, and then we begin with B1 of B2 of C1 of C2, and that is automatically 0, plus a sum over all the possible contractions, but where the contractions now are only between the chains of normal ordered operators. So I'm going to write this as all, and then there's a normal order product of A1, A2 dots of B1, B2, and C1, C2, and where the contractions now only take place between the operators in the normal order products, where the contractions are only running over contractions between operators from different normal order products. So I'm not going to prove it, but the proofs follows very much the same recipe which we did before. But this is something which simplifies considerably the calculations of expectation values. So the only contractions which survive, the only one which give non-zero, are those which involve contractions between operators from different chains of normal ordered operators. And you saw that if you go back to this example with the two particles which we had here. So the only contractions which are non-zero, so instead of summing up over all contraction, you only include those which are non-zero. And that means that you then need only to consider contractions between chains of normal ordered operators. And this is exactly what we had here. If we think of the state as a product of creation operators, which is already normal ordered, and a set of annihilation operators only, which is normal ordered by default. And then we have the operator itself, which is also normal ordered. So that leads to something which is going to simplify life a lot. And we are going to look at an example now when we calculate the expectation value of a two-body operator. And then you will see that there are only some specific contractions which survive. So if we try to take the contractions between the operator itself, a two-body operator, that will always give zero contributions. So generalizing Wick's theorem, the only thing which we need to take into account are the contractions between different chains of operators, which are already normal ordered. So this concept becomes even more useful when we move on to particle hole excitations, which is a way which allows us to simplify the calculations further, where we redefine the vacuum state. So I went a little bit over time. I would just suggest that we take a break, 15 minutes or something like that, and we stretch legs, and then just be back at 11:20, if that's okay. There's coffee outside here, or water if you prefer. And if you have questions, please feel free to ask questions. So I'm going to stop there. So when we now are armed with Wick's theorem and the generalized theorem, we are now going to look at some simple examples. And this is something which will also aid us in the solution of these exercises for this week. So keep in mind also that the exercises for this week with this Lipkin model is something which we most likely will not finish this week. And we will continue with that next week as well. And I was thinking that this could be one of the possible example cases we could use for the first midterm or the first project, because it has many nice pedagogical features. But let's take a look at some examples before we move on. So suppose now that we are looking at this two-body interaction, and this is something which is relevant for the exercise. And this two-body interaction is something which we are going to write like this. And we calculated the expectation value last week. But let's repeat it and then look at this in forms of Wick's generalized theorem. So we would then have an integral with some interaction. And then we have this creation operators, A alpha, A beta, A delta, and A gamma. So note that this operator here is already on a normal order form. So when we highlight this one, so this is what we would call a normal ordered operator. And one thing you also see here is that if I try to calculate this contraction, or I calculate this contraction, or this one, or that one, which are the possible ones, they are automatically zero. So a normal ordered operator, when I take contractions inside the operators, then it's always zero. Then, if we go back to this two-body state which we had, this infamous state which we have now, this is also given in terms of a normal ordered chain of operators. In this case, we only have creation operators, which means that when I now calculate the expectation values with alpha 1, alpha 2, and this operator H1 of alpha 1 and alpha 2 here, what I'm going to do now is simply just to look at the operators. So I'm skipping the vacuum state, I'm skipping the integrals and everything. So this is the quantity which is important for us now. If we now rewrite it in terms of this A alpha 1, it's actually an alpha 2 which we had, an A alpha 1. And then we have this next chain of A alpha, A beta dagger, A delta, and A gamma. And then we have the final piece, which is also normal ordered. If we then use Wick's generalized theorem, that means that we can only make contractions between the different normal ordered chains of operators. So we could have this contraction here, that's a possible one. We can have this one, and we can have that one. But we cannot have something which goes inside here or inside there. Or we cannot have this one or not that one. So that makes it easier when we now are going to look at this jungle of possible contractions, because there are many which we just can skip looking at. And when you now look at this set of operators which we have, there will only be 4 different sets which give us something which are different from 0. So last week we did calculate this one. So now I just wanted to show you how you can simplify your calculations by just looking at the set of normal ordered chains of operators. And that makes life easier when you are setting up all possible contractions, because else it's pretty easy to get lost and don't see the wood for the trees. So this is also something you will practice in this exercise which we have this week. And if you don't finish it, don't stress with that, because we will continue with this exercise next week as well. So that's just an example. So one other practicality, which is going to make life a little bit easier for us now, is a diagrammatic representation. So I wanted to introduce that before we move on to what is called the particle hole formalism. So the diagrammatic representation allows us to compactify the way we look at different expectation values. And it also allows us to introduce a kind of pseudo-like physics way of reasoning, because we can just draw a diagram for a physical process. And that gives us a compact and very easy way to discuss possible physical interpretations of, let's say, specific expectation values or transition probabilities. So you will often see when you do many body physics that you can express these quantities in terms of diagrams or figures, if you want prefer that. This was introduced by Feynman in the infancy of quantum electrodynamics, and it's been an extremely powerful tool to discuss and interpret physical processes. People have also tried to use the symmetries of the interactions and find out which diagrams should be there. So you can actually use results from geometrical topology and find out which contribution should be there. If you do many-body perturbation theory, which is one of the standard methods, you can actually find out which diagrams should be there order by order in perturbation theory. And that's something which people have implemented. So diagrams are a powerful way by which we can talk about the physical interpretations of a specific process. So let's introduce a diagrammatical representation before we move on, because this is a tool which you will see in basically all textbooks. And the textbook which I'm linking to is this textbook which you also find online here, this textbook by Shavit and Bartlett. And if you go into the GitHub address and you go to many-body book here, no, not that one, sorry, that was not the one I was aiming at. If you go in here, you will have a link to, there should be a link to the literature here. Literature, there we have it. And here we have this textbook by Shavit and Bartlett, which uses extensively this kind of diagrammatic language. And chapter 3 here introduces some of the basic notations, which I will also be using here. So let's go back to the whiteboard and look at the basic diagrammatical notation which we will be using. So just keep in mind that at the end, you have to calculate something. But diagrams is just a useful pedagogical tool. That's the way I view it. So you would then start with the simplest thing, which is a contraction. So you have an A alpha dagger like this. This is something you would write as an arrow. And depending on how you let time go, you could think of time going from a state alpha, which is being destroyed, and then you create a new particle in a state alpha. So diagrammatically, you would typically represent a contraction with something with an arrow, and you would write an alpha here. So when you have performed a contraction, I'm going to put an arrow on it. And you could think of this as something which moves forward in time. So it gets created at a specific moment, and then it gets destroyed afterwards. Now, you can then, we are going to let the arrow, when it points up, and this is something for later when we have introduced particles and holes. So this is generally going to be what we were going to call a particle state. So in our case, with vacuum, with the vacuum state, all states are particle states. We create a particle with a given set of quantum numbers. And then if we have an arrow which points down, like this, then this is going to be called a hole state. And this is a state below the Fermi level, which has been vacated. So that means that you have kicked out a particle state from below the Fermi level to above the Fermi level. So you leave a hole state. And that's why they're called holes. Now we come back to this formalism tomorrow. So there's a hole state. So this refers to states below the Fermi level. Below Fermi level. And in order to do that, that means that sorry, this should be level, not leveled. So state. These are states below the Fermi level. And this applies to a redefinition of the vacuum state. So that means that we redefine a new vacuum. And the new vacuum, or reference state, as it's often called, is going to be the state you can make by filling up all single particle levels up to the Fermi level. So we are going to look at how we can redefine the vacuum. And that's going to give us a more compact way of performing calculations and interpreting physical processes. Now, for those of you who are familiar with quantum field theory, so how many of you have taken, I know that one of you have taken quantum field theory, two of you. So we are not going to have antiparticles. So in quantum field theory, a state with an arrow down, or the whole state as we will use them, they will typically be given the name of antiparticles. So we are not going to have antiparticles in our system, mainly because we will essentially stay with non-relativistic quantum mechanics. And the energies which we are going to look at will be of such a size that we can never create antiparticles, because we will typically be dealing with low energy systems. And the excitations, like in condensed matter physics, atomic physics, will typically be of the size of electron volts, which is the typical energy scale in atomic, condensed matter, and molecular physics. If you go to nuclear physics, where you can also use much of the formalism, we are talking about mega electron volts. But still, it's much less than the total binding energy of a nucleus, which is in the giga electron volt region. So typically the systems we would deal with compared to the total energy of the systems are going to be systems which we can classify within the formalism of non-relativistic quantum mechanics, which essentially means us solving Schrödinger's equation for many particles. So it's an important distinction between what some of you have seen in quantum field theory and what we are going to deal with here. Okay, so these are the notations which we will use. And then if we look at an operator, so a one-body operator, and the typical example which we have been looking at is given by H0, which is a sum of all these alpha betas. We have this integral and multiplied with A alpha and A beta here. This is something which we would represent diagrammatically. And we have, in this specific case, because we haven't done any contractions, we don't have any arrows on the lines. So what we're doing now is that we are writing this in the following way. So could you just close the door in the back there? Because it gets a little bit noisy here. So this would be an incoming state beta. And this is the outgoing state alpha. And this blob, which you see here, this is going to be named an interaction vertex. This quantity here is something which represents the operator, H0. And then the quantity you see here now is then something which represents this alpha of H0 or beta. So when you're now looking at this specific term here, that is something which now this specific diagram refers through the term which you see here from this part, which is called the vertex. This represents now the specific matrix element which we have. So by looking at this one, you can then just read off this specific element here. And then this line here is a state which comes in. So you can think of the system being in a state beta, and then it transits to state alpha. So what you would say then is the following, is that the outgoing state alpha or outgoing alpha represents this specific term, and then the incoming state, incoming beta, that represents this state here. And then the circle is normally called a vertex. And since it's a one-body operator, it acts only at one particle at a time, and then we just have one dot here. So that's the one-body operator. And then we have a two-body operator, which is the next step. So two-body operator, so let's just write that one. Oh, did I go too fast? Did you get time to write this down? Okay. So if we then do the two-body operator, what we have then is something which has an alpha beta V of gamma delta, and then we have these operators A alpha, A beta. This is the general form which we have of A gamma. And we would typically write this as follows. So we have two interaction terms because we have two particles interacting. And then we have a dotted line to indicate the operator itself. So this will be over V. And then we have a state coming in, and we're not putting arrows because we haven't done any contractions. So I have an incoming state gamma and an incoming state delta. And then I have an outgoing like this. So when you now look at this one, you see that this state alpha beta, this is given now by the, so the left position is the state alpha, and then the right one is the state beta. So the state to the left in the diagram is the state alpha, and the state to the right is the state beta. Then these two together, they define this outgoing state, which is a two-particle state. So you could think of this as your interaction now, having an incoming state. The particles are in a state gamma and delta, and then something happens, and then the system ends in a state alpha beta. So, and you would have the same with the gamma delta here, where the left one corresponds to gamma, and the right one is now this specific single particle state delta. So you would have an operator line, which is the line here. So this is a typical way we represent a two-body operator. Body operator. So that's the operator itself, which then acts on some specific states. So when you see a diagram like this, what you would say then is that, okay, this diagram here is now something which represents a two-body operator. We have an incoming state, gamma delta, which then gets affected by the operator, and we have an outgoing state, alpha beta. So we're not putting arrows because we haven't done any contractions. So let's now move to the next thing, which is a specific state. So this will be 4. And the specific state, if we now have a state, let's say alpha beta, we are going to label this one in a specific way because this is also the way Shavit and Bartlett use it. So you could think of this as your vacuum state. So this is just a plain emptiness, this line here. But it could be a reference state where you have redefined your vacuum state. And now, since this one is equal to A alpha, A beta, acting on 0, you're just going to put 2 lines here. So this is alpha beta. And then if I look at the other state, if I take alpha beta here, this is the same as, and now we are having the vacuum state here. So we are ending back into the vacuum state. And then I have the states alpha and beta, but that is given by 0. And then I have A beta, A alpha. So these are just definitions. So when I now calculate an expectation value, I can actually look at this diagrammatically. And you will see how this can be used to simplify and see the contractions, which when you write everything out, it looks like as a jungle of contractions you have to make. When you draw the diagram, everything looks a little bit simpler. So that's the pedagogical aspect of a diagrammatic representation. So let's now look at a specific expectation value and take an example here where we use these rules 1 to 5. So let's now calculate this expectation value with a two-body operator of h of I of alpha 1 and alpha 2 here. So this is the matrix element we've been looking at. So if we take that specific matrix element, what we would have now is the following drawing. So we have the vacuum state we begin with here. So we have 0. And now we have this specific state, alpha 1 and alpha 2. And in between now, we are having the interaction. And I have, no, I shouldn't put arrows, not yet. And then I have my gamma and delta. And then I have the two outgoing states, alpha and beta. And then this is going to end in a final state. So this is my vacuum state. And I have an alpha 1 and alpha 2 here. So when we calculated it, what we had was A alpha 2, A alpha 1, and then I had A alpha. Well, let me just put it up in a different way. So what we calculated was A alpha 2, A alpha 1, A alpha, A beta, A delta, A gamma, A alpha 1, A alpha 2, and dagger. So these are the quantities which we calculated. And then we looked at these contractions here. It's a possibility. Or let's rather take the one which we started with. So we have an A alpha 1, an A alpha. So the quantity which we looked at first was actually this quantity here. Now, if I now want to make a drawing here, what I'm going to have is now this contraction here. And I get this contraction. And I get this possibility. So diagrammatically, what you see now is that you're visualizing, in a certain sense, a physical process. You go from a state alpha 1, alpha 2, there are some interactions, and you end in a state alpha 1, alpha 2. So the contractions which you're seeing now are obviously mathematically given by delta alpha 2, delta. I have my delta alpha 2 of beta, and then I have my delta of gamma of alpha 1, and then I have my delta of alpha. These are the Kronecker deltas. So each one of these contractions is going to give me a line with an arrow, as we put it here. And since these are states all above the vacuum state, the true vacuum state, they're all particle states, so we will use an upgoing arrow. So what happens then is that this specific example we have, this is going to give us a matrix or a diagram, which looks like this. And now I have performed the contractions. So this is alpha 1 and alpha 2. And this is alpha 1 and alpha 2 coming in. So the diagram rules, which you then use, is that when you have performed such an expectation value, that's when I'm putting the arrows on them, because then each arrow represents a contraction I've made. And then you can then, from this, you can just read off the matrix element immediately. So if I use the rule for the matrix element now, I would have alpha 1, alpha 2, of V, alpha 1, alpha 2. Does that sound reasonable? So I'm just setting up driving rules here. And that allows us now to express in a more compact form these type of integrals which we had previously. So when I performed the contractions last week for this specific term which you see here, then I actually got this term. So what I'm doing now is simply to look at the contractions in this specific way, diagrammatically, and that gives me this term, which represents now in a very compact way all these calculations which we did here. And then we simply end up with this specific integral. I can now obviously do other contractions. So there's nothing which hinders me that I contract this one with that one, and I contract that one with that one. They are fully viable. And I could keep this one. That will give rise to what we call the exchange term. And diagrammatically, this is also written in a specific way. So if you now look at the contractions here, suppose now we look at the term which is going to give rise to the exchange term. So this is what we call the direct term. And if we now take the exchange term, what we still have this vacuum state. We have the state alpha 1 and alpha 2 without the arrows. We have the interaction here. And then we have an alpha, beta, gamma, delta. And then I have my vacuum state. And then alpha 1 and alpha 2. But now I can perform a contraction with this guy and with that guy. And I can still keep these two guys here. That will give me now a matrix element when I do the set up the specific matrix elements, which looks like this. And I have an alpha 2 of alpha 1. That's the exchange term. When I look at the diagram, I can calculate it or draw it in the following way. So I would have arrows, and then I have alpha 1 and alpha 2, but then I have alpha 2 here and alpha 1 due to the contractions which I made. So originally, the way I have organized the states is that I have organized the states so that I have alpha 1 and alpha 2. So if I want to rewrite this one, it will come with a minus sign in terms of interchanging alpha 1 and alpha 2. So that means that diagrammatically, I can draw this one in the following way. So I can have, I wish to keep the order which I set up. So I want to have alpha 1 to the left and alpha 2 to the right. And then I would have this case here. So that's the exchange term, alpha 1 and alpha 2. So that means that when I want to represent the fact that alpha 1 has changed place with alpha 2, I have a crossing fermion line. And that gives rise to a minus sign. Because this term here comes with a minus sign when I do the calculations. So if I go back to my contractions, that means that here I now have this contraction here. And when these two guys here cross, that means that that gives rise to a minus sign because we want to bring the operators close to each other in order to calculate the expectation values. Diagrammatically, that is reflected in crossing fermion lines. And that gives rise to a minus sign. So that means that when we then calculate the final contribution here, when we do the final one, what we have is that alpha 1, alpha 2 of HI, as we calculated last time, theoretically, when we then run through the calculations with all the contractions, this was given for this specific case in terms of the direct term, and then we had the exchange term, and V of alpha 2 of alpha 1. Diagrammatically, this is going to look like this. So I can just read off from the diagram that here we have alpha 1 when we put labels. And here we have alpha 1 and alpha 2. But then here we don't put a minus sign, because the minus sign comes when we are going to set up the expression from the diagram. So we would have these two crossing fermion lines. So we would have an alpha 1, alpha 2, and then I have my alpha 1 and my alpha 2 here. So this is the way I would represent diagrammatically that specific expectation value. That sound reasonable? So these are just the rules which we're going to use in order to extract from the rules, because when you have these diagrams, at a certain point you have to calculate something. And when you calculate something, you have to turn these into mathematical expressions. So you can't feed in this. Maybe you could have fed in these pictures to a code, and then you have a convolution neural network which recognizes what this means mathematically. But you have to translate this into some mathematical expressions. So the driving rules here is simply that when you have a crossing fermion line, that means that you're then getting a minus sign. So the crossing fermion line here, that gives rise to a minus sign here. So crossing fermion lines. And then we are placing the states in the specific integral we're calculating, so that we have an outgoing state to the left, which it becomes the first here. And then we have an outgoing state to the right, which becomes this one. And then finally, we have the incoming state here. But now this incoming state is actually the state to the right. And you see that here. And then you have the incoming state to the left, which is this one. And similarly for the previous diagram. And later, when we are going to deal with many particles, we will find it very convenient to introduce the particle hole formalism. So let me just give you that as a mini motivation for what is coming tomorrow. So you will see quickly now that if we deal with many particles, and in the exercise, which we have this week and also next week, we are calculating the expectation value for a 4-particle state. But suppose you have 10 particles now. So with 10 particles, you would have something like this, up to some alpha 10. So you have alpha 2, alpha 3, and this goes up all to alpha of n. And then we have an interaction here. And then we have an initial state, which looks like this. And here, so we have an alpha 1, alpha 2 here, alpha 3, alpha 4, then alpha 8, alpha 9, and then alpha 10. So these lines, all these lines may actually interact with interaction. And you have 2 at a time, which then would be contracted with the 2-body operator, because the 2-body operator acts on 2 particles at a time. And then we would have a contraction here with this one and that one. Now, what you see now is that this becomes very quickly something which is almost impossible to keep track of. So if I were to give an exercise where I wanted you to use a diagrammatic representation of Wick's formalism and so on, and calculate the expectation value of a 10-body state with a 2-body operator, you would not like it that much, because in a way, this is a very clear case where you will get lost with indices. So even if we have introduced Wick's theorem here and have simplified the way we deal with the calculations, we can actually further simplify the calculations. And this is what is going to come tomorrow. And the particle hole formalism, or us redefining the vacuum, is a way to actually simplify these type of calculations. So as soon as you move beyond 2 or 3 particles, this becomes a very, how to say, unwieldy way of calculating expectation values, whether we are dealing with the contractions or if you're just dealing with a diagrammatic representation. So if you look at this here, this means that instead of having a 2-body state here, which we had here, we would have a 10-particle state or 10-body state. So that means that you would have 10 creation operators here, and you would have 10 annihilation operators here. And then you would have to look at all the possible contractions. Now, these contractions are easier in a certain sense because the operator acts only on 2 at a time, but you would have to set up all the pairs of contractions which are possible. And that bookkeeping can be done, but it's tedious. So I hope you see that as soon as you have 10 operators here, even with a 2-body operators, you get too many terms to deal with. And it's not fun to do it. You can do it, but you should rather automatize it. But there is a formalism which allows us now to, well, it's not a formal, it's a kind of formalism, but what this formalism means that we are just rewriting or redefining the vacuum state. And what we will deal with now is actually, and that's the next piece, which we are beginning with tomorrow, that is the particle hole formalism, where we redefine the vacuum. So that is basically redefine the vacuum state. And we are going to define a new state, which I'm just call a C for a core state or reference state. It has many different names. And that will simplify the calculations, and it will introduce a language where we are describing a physical system in terms of what we will call particle hole excitations. And it's a convenient way to restructure the way we look at different types of excitations of the system. So I hope you see the kind of complexity you would get. You can do it, but it becomes quickly, not very practical. Even if you draw the diagram, say, you still have to draw all the possible combinations of pairs. Should we stop here? Is that okay with everybody? And then we pick up this thread tomorrow? Okay. So don't hesitate to ask questions.